Hey, welcome back everyone into the Wells Tech Garage. Thanks for joining me again tonight for episode number 2 of this little mini series. If you missed last night's episode, make sure to go back and check that one out to figure out how we got to this point. But just a quick summary, we have an 07 4Runner here with a P0016 cam crank correlation on bank 1. And the testing that we're going to do tonight is not only applying to this vehicle, but you can do this test on any vehicle as long as you have the tools that we're going to be using. So let's get right into it. So we left off where we needed to diagnose this vehicle beyond any sort of doubt. We need to take our check engine light and we need to be able to go up to the customer or have our service advisor go up to the customer and sell the job 100% without question, okay? We can't be parts changers. We can't just load up that parts cannon and launch a couple of cam sensors or a crank sensor at this thing before we know what is potentially causing our problem, okay? So here's Toyota's diagnostic for a P0016. Step 1, check valve timing. Check for a loose and a jumped tooth of the timing chain. So A, remove the cylinder head covers, so valve covers, right hand and left hand. Read through all this. They're having you physically check the timing. If it's bad, adjust the valve timing. If it's okay, replace the ECM. I can't tell you guys how much of a problem that I have with this. First of all, step 1, remove valve covers? Seriously? Let's talk about a scenario. Customer comes into the shop, intermittent check engine light on, right? Service writer writes up the ticket for a 1-hour check engine light diag. So as a technician, we're getting paid 1 hour to diagnose this vehicle. Car comes into your bay, you pull the codes, find out that it's a cam timing correlation code, okay, between bank 1 cam and the crankshaft. So you look at Toyota's diagnostics and they want you to, first of all, check the valve timing. Check the cam timing, so you're supposed to pull the valve covers off. Well, according to book time, you find that that's a 2.3 hour job just to R&R both valve covers, let alone verifying that timing. So I'm supposed to dive into this motor, rip the intake off, rip the valve covers off, 2.3 hours worth of labor on a 1 hour check engine light diag. It's not going to happen. I'm not doing it. I'm not going to physically check the timing on this motor. There's no point. Why? And besides, what if the timing's on? What if we go to the customer and approve 2.3 hours of checking the timing for it only to be right? What if the timing's accurate? What if the timing is right on like it's supposed to be? Who pays for this then? Why are we getting our hands dirty? Why are we diving in head first before taking a second to think about what we're looking at here, okay? This is where working smarter, not harder, really comes into play. And hopefully, at the end of this little mini-series, you guys are going to have a handful of tests that you can do when you have this exact same problem. So the first one that I want to do is relative compression. Because, in theory, if we have a single camshaft on a V6 motor that's off a tooth or 2 teeth or 3 teeth, whatever it is, in theory, the compression for that entire bank should be different than bank 2, okay? Bank 1's compression should be different than bank 2 because our cam timing is off. We should see those 3 cylinders looking different. So you could hook up a compression gauge or a transducer and measure compression on all 6 cylinders, but R&Ring of the plugs on this vehicle is 0.9 hours. So just under an hour to R&R the plugs. Now that's without hooking up the compression gauge. That's without putting any pressure transducer. I'm not wasting that time. I don't want to pull all this stuff apart. Let's do it electronically. Let's do a relative compression test. Now, for those of you guys out there that are working on Fords, it's really simple. You go through with the scan tool and you can perform a relative compression test with the scan tool. It's great. If you don't have that ability, get out your lab scope, hook it up, and in under 10 minutes, you'll have a relative compression test that not only can you feel proud of that you did, but will hopefully give you an answer, okay? So this is the setup. We have our V6 engine, and we want to throw an amp clamp around our battery positive wire that goes down to the starter, and obviously our battery is grounded to our engine at some point. So here's the goal. As the piston goes down on our intake stroke, it starts to come back up on our compression stroke. We're current clamped around our starter cable, so we should see a peak in amperage as that piston comes up inside the cylinder on compression. That's going to be the hardest point for that motor to turn. So we should see a peak in amperage on our amp clamp. Then as that goes into power stroke, we should see that peak drop down. and then we go through the stroke. We end up in the exhaust stroke. Our piston's on its way back up. We're traveling up, but now our exhaust valve's open. So we should not see a peak for that. And then we have our intake stroke again, and then we have another compression stroke. So this is what it should look like for a single cylinder engine for a rough, drawn up relative compression, okay? For V6, you would expect to see something like this. All 6 of your cylinders in line with roughly the same peaks. Remember, we always want our compression within a certain percentage of each other. Relative compression is going to be the same. It's relative to each other. It's relative to the draw against the starter, which would draw from the battery. So if both both cams were off on this engine, if they were both off the same amount, relative compression wouldn't give us anything. If the entire engine's compression is down, we're not going to be able to find anything with relative compression because it will look the same. But if we have one cam that's out, there's a high probability that bank 1's relative compression is going to be lower than bank 2's relative compression, okay? So what do we got to do? We got to set up our scope. We want a relatively long scale for our time. Voltage scaling is going to vary depending on how you're setting up, because remember, we're using an amp clamp. We need to convert our voltage. We need to look up the firing order of the vehicle, and we want to set some sort of trigger. And basically, we're going to look for reoccurring higher or lower peaks, okay? So I set an ignition trigger. This is, your common ignition diagram. They're going to share a common power. We just want to hook into one of our coils, one of our ignition coils, and all we're doing is trying to just figure out where that engine is so we can lay timing onto that, okay? So that way we know, according to our firing order, which cylinder we're on, so that way we can lay it all out. And I'll get to that in just a second. So what we're going to do is get right into it. So in order to do this test, you need at least a 2-channel lab scope. 2 channels or better. You need a high amp clamp. This is the clamp that was sent with the Pico kit. This is a 2000 amp clamp. I'm going to go ahead, I'm going to set it on that 2000 amp scale, zero it out, and I'm going to put it around our positive battery cable. Make sure it's all out of the way there. And I'm going to hook this one up to channel A on our lab scope. And I'm going to take our second lead here. And now this is going to be our ignition trigger. This is going to be what is going to tell us where the engine is at that time. So we know that the ignition coil should fire just before top dead center on the compression stroke of whatever cylinder that you're on. So we should be able to see where this thing fires, lay the firing order over this graph that we're going to get, and know exactly what cylinder is what for our peaks of our amperage, okay? So I'm going to go ahead and grab a back probe here and throw this ground clamp on the ground of the battery. And now, a lot of times you want to grab cylinder 1 for this, so you know that it's cylinder 1, but it doesn't matter really which cylinder you grab. I'm going to grab the easiest one, which just so happens to be cylinder number 4 over here on this engine. It's the easiest coil to get to because these things are kind of sitting underneath the intake manifold. So I'm going to go ahead and back probe in there. And there we go. Okay, so what if you don't know what coil's what? You need to know that before you go ahead and do this. Now I'm going to hook this up. So I know this is coil 4 because I looked up our firing order and cylinder location. But if you would want to do that, head out to our website, wellsve.com. This is free for anybody. Go to Search Parts Catalog. And we're going to go down to Search by Vehicle. We're working on an 07 Yoda 4Runner with the 4-liter V6. Okay, now this is our catalog. If you guys aren't familiar with this, you can find all of our part numbers in here depending on what you're looking for. And what we want to do is we want to go to firing order. Click on this. We're working on a Toyota truck, 4-liter. Click View. And there we go. An 03 to 12 Toyota 4-liter. Coil on plug. Here's our V6 engine. Here's our firing order. Cylinder 1, 3, 5 on bank 1. And cylinders 2, 4, and 6 on bank 2 with a firing order of 1, 2, 3, 4, 5, 6. Okay? So I'm hooked right now into the ignition coil on cylinder 4. So when we overlay our firing order, we'll know that our ignition trigger is on cylinder 4, and we can go from there. Let's go ahead and open up our scope, and let's get this thing all set up. All right, for starters, I want to go ahead and turn on both channels. All right, both channels are turned on. Let's add some labels to this. So channel A is going to be the starter motor current, because again, we're using a current clamp. Channel B is going to be cylinder 4. Actually, let's just go ignition. And we'll just go primary voltage, and let's just note that this is cylinder 4, and starter motor current, we'll leave that alone. All right, now we need to turn our scope on and tell it that we are using a amp clamp. And we're using a 2000 amp clamp in the 2000 mode. And let's grab some specs here. Let's go 0 to 500. And let's throw this on a scale, a 2x scale. So now let's put our 0 mark. Okay, so this is our 0 line, and it looks like we're recording up to a total of 315 amps. And let's grab this, and let's just throw this on 20 volts right here. So now we should see our coil come on and off for cylinder number 4. And let's up our time scale. Let's go to 500 milliseconds per division. So now we have a long time scale. On the screen here, we're looking at a 5-second total window here. And what we need to do now is we need to crank over this engine. We can't have it start up. It's not, relative compression is only during engine cranking, okay? So you need to disable something, either fuel or spark, or you need to put the thing, foot pedal to the floor, a gas pedal to the floor, and put it in clear flood mode. Whatever you want to do to get it to happen, we need to make this thing not start. So what I'm going to do, because it's easy enough, I got a relay box right here. I'm just going to grab the fuel pump relay out of here. And then I know for a fact, no matter what I do, this thing's not going to start. So fuel pump, thank you for Toyota for labeling this very nicely. And there we go. Fuel pump relay is out. Our scope is all set up. So at this point, it's time to crank it over and see what we got. Now there's a high probability that this thing is going to start because of the fuel that's stuck in the rail. So I'm going to start it and then shut it off and then re-crank. Let it stall out. Maybe. There it goes. All right, so it's stalled out. Now we're just going to crank. Oh, still some fuel in the rail. So what you want is a very consistent cranking. And it's also, just to add a note in here, throw a battery charger on it. You want your cranking as consistent as possible across all 6 cylinders, okay? So I have a battery charger hooked up to this thing to maintain our battery at peak voltage. Let's go ahead and see if we can get a cranking pattern now. Oh, still a little fuel in there. There we go. All right. All right, I'm going to give it a little gas to try and clear this thing out a little. All right, there we go. I'm going to shut it off and I'm going to do it again. All right, that was a good one right there. We'll save that one. So go ahead and pause the scope. And let's backtrack a couple here. All right, that was perfect. I like that one right here. We had nice consistent cranking. It seemed to be going roughly the same speed for the entire time. Let's up our scale here, make this a little bit bigger, easier to read. Let's change our scale here. Okay, so what we have is, and let's zoom in on this. Let's grab a couple. Okay, get this out of the way. So what we have, guys, is our amperage waveform here and our cylinder 4 ignition right here. So this is our trigger. So we should have 6 peaks between our triggers. So cylinder 4, and this firing order was again 1, 2, 3, 4, 5, 6. So we have cylinder 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, sorry, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Okay? So by just taking a quick glance at this, it's hard to tell exactly what we're looking at. Let's zoom in a little further. So here is a full cycle. So cylinder 4, well, let's go like this. Let's grab a screenshot of this, copy it, and I like to use paint. There we go. So just to make this even easier, let's grab this. Let's go like this. This is cylinder 4. This is cylinder 5. This is 6. 1, 2, 3, 4, 5. Okay, so this is our firing order. And again, we looked that up out on our website and found firing orders 1, 2, 3, 4, 5, 6. So cylinder 4 is our trigger. That's what we're hooked up with our scope lead on the red channel. So we have 4, 5, 6, 1, 2, 3, 4, 5, and then 6 would be over here. So now what I want to do is I want to see where these peaks lie with each other. So what I'm going to do is I'm going to grab just a flat line. I want this line as flat as possible. Right about there. All right, nice flat line. And I'm just going to drag this up here and see what we've got. All right, so I'm going to carry this up to the peak of each of these. There we go. So cylinder 4, nice and high. Cylinder 5, a little bit lower. Cylinder 6, almost right there. We'll drag it down. Almost right there. Cylinder 1, a little bit lower. Cylinder 2, right back there. Cylinder 3, a little bit lower. What is this showing? 5, 1, and 3 are all on bank 1. 2, 4, and 6 are on bank 2. So this potentially shows that our current draw, 4, 5, 1, and 3, are lower. It's not drawing as much current, so that must mean that our compression is lower on there, right? It's easier for the motor to spin, easier for the starter to spin it over, therefore less current draw. So 5, 1, and 3 have lower compression. But let's take a look at another one here. Let's grab another pattern and see if this is consistent. All right, this one looks pretty decent. No, it looks like it shut off or tried to start right there. All right, this one looks pretty good. Let's grab just another single cycle. Oh, I can see that already. Look at this. So this is cylinder 4, remember? Let's just bring it back into paint. Let's do it again. So I'm just going to copy and paste, bring it into paint. I'm going to paste it in there. And let's throw some labels on there. This is 4. Because again, it lines up with our ignition trigger. This is 5, 6, 1, 2, 3. This is the easiest firing order ever. They're not always this easy. All right, so we'll be happy with that. 4, 5, 6, 1, 2, 3. Let's make another one of those black lines so that we can have an idea of what we're looking at. Oh, a little bit crooked. Okay. Look at this one. This is even more obvious, right? So here's our peak for cylinder 4, cylinder 2, and cylinder 6. We'll just go with the lowest, cylinder 6. So that's the peak amperage for 4, 6, and 2. Look at 5, 1, and 3. Look at how much lower these are. Look at how much higher 4, 6, and 2 peaked. All right, so by performing this relative compression test, I'm relatively certain now that we have a problem with bank 1. I don't know 100% yet if our timing chain has jumped, but I know that our compression is low on cylinders 1, 3, and 5. It's lower in relationship to cylinders 2, 4, and 6. Now you could get out a compression gauge and you could thread it into the hole and do all that work, but do you really need to at this point? We just proved on this graph here that cylinders 1, 3, and 5 are lower than cylinders 2, 4, and 6. I don't really care how much lower. All I know is that they're different, and it's on the bank that we're setting a check engine light for. So at this point, I'm maybe 80, 90% certain that our timing has jumped on bank 1. But I like to be 100% certain. I don't like those small percentage what-ifs to come back and bite me in the end. So that's what tomorrow night's going to be. Tomorrow night, we're going to be 100% certain in tomorrow night's class that our problem lies with bank 1. So make sure you guys come back here tomorrow night, same time, same place. We're going to look at this system exactly as how the computer tests it for that P0016 code. So thanks for watching. We'll see you tomorrow night.